So I described the salinity variation with just words, right? So now let's look at some figures. So here is a figure of Earth showing part of the Earth and the so-called meridional profile. What do we do? Basically, we take all the longitudes, we average along all longitudes, and we are left with just latitudes. This is called the zonal mean meridional section. So some zonal mean meridional section of temperature and salinity is being shown. So you're going from the equator in the middle to 90 north and 90 south, and you can see that there is a slight asymmetry in the salinity. In the north you have much less salinity at higher latitudes than in the south, and the minimum salinity is actually not on the equator, is slightly off the equator. We will see later on why that happens. And the temperature also is not perfectly symmetric, but we will see again that, well, actually you already know why that could happen, because the southern pole, South Pole, has Antarctica, which is a continent, which means you can build a big glacier. So there is several kilometers thick glacier sitting on the South Pole. So the ocean is the Southern Ocean, which is at a lower latitude than near the pole, whereas in the north you have Arctic Ocean that covers the North Pole, even though there is a lot of sea ice there as well. We'll see later on that actually sea ice can never get as thick as a glacier on land, right? We'll see what the reasons for those are. Nonetheless, tropics are warm, and the temperature begins to drop as you go to higher latitudes, and the salinity is minimum of the equator, where the rainfall is maximum. So we essentially have to look at evaporation and precipitation together to determine what is the net impact on salinity. So in the tropics, as we said, there is more precipitation than evaporation, so they are wet latitudes, so you have low salinity. In the evaporative latitudes in the subtropics, you have the maximum salinity, and then you have rainfall that is being created by the water that's being exported from the evaporative latitudes, and you have sea ice formation, sea ice melting, some glacier discharge, some river discharge, and so on and so forth. The Southern Ocean doesn't get as fresh because it is still an ocean, not as much continent as in the Northern Hemisphere, not as much sea ice to melt, and also not as much rain at those latitudes. So we are getting much closer to like 70 south here and 70 north here, and not going all the way to the pole. Here Antarctica prevents us. Here we are basically not going into the Arctic, which is a mix of sea ice and so on. Okay, so this is the salinity distribution. You can also look at a map of salinity. There is a new satellite that was launched in 2011 that flew around for a few years, and then it died. Was called Aquarius, was a US Argentine satellite that was measuring salinity from space. It was basically relating the properties, radiance. Every satellite basically looks at the light that's coming from the ocean surface in different frequency bands and relates it somehow to conductivity for measuring salinity, to waves or temperature, and so on and so forth, right? There are also ways to measure other quantities like chlorophyll, etc. So here the map for a couple of months in 2011 is a good indicator of the typical salinity distributions we get in the world ocean. So what do you see? You see, first of all, that the evaporative latitudes have higher salinity than these blue regions, which have low salinity, where the precipitation exceeds evaporation. And you will see immediately that the Atlantic seems much more salty, as you can see on the scale here on the right side in parts per thousand, as we discussed before. And the Pacific evaporative latitudes are higher than this long band we will come back and learn later on, called the intertropical convergence zone, where a lot of rain happens. And where we said rain also happens. And the higher latitudes, the Arctic is very fresh compared to the Southern Ocean that we already talked about. There are lots of these features in it that we won't discuss. And the reason why Atlantic has got higher salinity is, of course, because it's got land so close to it on either side, as opposed to the Pacific, which is vast. Remember, we said Pacific occupies almost 50% of the surface area of the oceans. The dry air that will come off from the Sahara, for example, is going to pick up a lot more moisture, and similarly here, air coming off from Africa is South Africa is Southern Africa is going to pick up a lot of moisture. The Indian Ocean has got a very nice contrast as well. Mediterranean is also a highly evaporative basin. In fact, loses water every year, which is compensated by the rivers coming in. So it's an evaporative basin. We'll see when we do regional circulation that Mediterranean has a very weird circulation because it's evaporating a lot and creating heavy water. In the Indian Ocean, Bay of Bengal gets lots of rain and a lot of rivers, right? Ganga, Brahmaputra are coming in, Krishna, Godavari, and so on and so forth. Whereas the Arabian Sea is a much more of an evaporative ocean. It's not getting as much rain as the Arabian Sea. So there is a stark contrast there, right? We'll see that the Indian Ocean circulation is very different because of the monsoon, because the continent is so close to the equator. You have the so-called monsoonal circulation, where the winds change completely in direction. We discussed that in the explorations part, where the Arabs were using the seasonal changes in winds to go towards India in the summer and back towards the Middle East in the winter months, and so on and so forth. So this is a quick view of how atmospheric circulation and oceans evaporation together are producing these large-scale salinity patterns. As we said, this also matters for oceans circulation, which we will see later on. How does salinity vary with depth? You can see here you are showing a high latitude profile on the left and a low latitude profile on the right. So compared to the high latitudes, where the surface is quite fresh because of precipitation, sea ice melting, etc., there is a nearly vertical profile, which means near the surface the winds are mixing the ocean and creating a homogeneous region near the surface, and then salinity increases very rapidly over this band called the halocline, shown in this orange color. Cline, like incline or decline, is a gradient. Halo is a Greek word again for salt, so halocline is a salinity gradient. There is a parallel thing in temperature called the thermocline, which we will learn later on. So then the deep ocean remains nearly at the same salinity all the way to the bottom. And you can see that both the low latitude profile and the high latitude profile reach similar values at depth, and then the deep ocean is at similar values. The surface salinity is much higher in low latitudes. Again, you have to distinguish between the evaporative latitudes and the tropics, but nonetheless this is some kind of an average, just to give you a sense that low latitudes have very high salinity at the surface and high latitudes have very low salinity at the surface. The difference doesn't seem like much, but combined with temperatures, cold temperatures, low salinity, so density is going to be increased by cool temperatures but decreased by lower salinity. In the low latitudes, high salinity would want to make the density higher, but warm temperatures would decrease the density, and so on. Okay, the seawater density, fresh water, we know is this 1 gram per centimeter cube. Ocean surface water, we said, is heavier because of salts in it. So surface water is 1.022 to 1.030, so just a small deviation from pure water. but this creates the so-called stratification or layering of the ocean, which you can see here. Basically, if you add temperature and density to it, basically you have ocean layered into different densities, changing little by little, so increasing with depth little by little. Low densities near the surface, increasing densities with depth. Remember, we said Earth is also stratified. As you go deeper, it gets warmer into from the crust into the mantle, inner core, and so on and so forth. Okay, so seawater density increases with decreasing temperature. This has the greatest influence on density because it has a large range. Salinity doesn't vary by that much, but we'll see that this behavior is very non-linear, makes for very interesting behavior of the ocean water because of this non-linear dependence of density on temperature and salt. So density increases with increasing salinity. If you add more salt, water gets heavier. And density also increases with increasing pressure, but we consider ocean to be nearly incompressible, which means the pressure doesn't affect the ocean density too much. So that makes for some simplifications when you want to solve the equations of motion. If density doesn't vary too much because of pressure, and if water can be considered incompressible, then the equations that govern the dynamics of circulation become somewhat simpler. We won't get too much into the dynamic equations, but nonetheless we'll return to this idea of incompressibility a little bit later on.